Hi everyone, we're just going to wait a couple additional minutes until start of the hour, and then we will kick off the presentation. All right, I think now is a good time to start. Thank you everyone for coming to today's webinar. Hosted by Zygo, we're going to be discussing performance surrounding aspheric surfaces and the metrology of how to acquire data on those types of surfaces. So join with me today is going to be Erin McDonald. She's going to be the Q&A chat moderator. Brief introduction to myself and Zygo. My name is Matt Battistoni. I am a sales engineer working out of our West Coast regional office in Santa Clara, California. Some of you who are in the webinar today may have interfaced with me throughout the years. And if not, welcome, and it's nice to have everyone here today. Erin is in charge of our Laser Interferometer product line. And if you guys have any questions that were not answered throughout the webinar here today, please feel free to reach out. Our contact information is going to be right here, but also at the end of the webinar. So feel free to jot that down or email us direct at our Zygo website. So before we dive into the topic of Aspheres, I did want to discuss, just give everyone a background history of Zygo. Some of you in the meeting today may not be familiar with kind of what we do and kind of what our spiel is. So Zygo is considered to be a market leader in our interferometric metrology instrumentations. There's two product lines in that category, really. There's an optical profiler and a laser interferometer. In addition, we make displacement measuring interferometers as a part of our PPS product line. But beyond that, we are also a optics manufacturer. So being that this is, a meeting surrounding aspheric surfaces, I'd be hard pressed not to discuss our facility out in Richmond, California, which is kind of a world leader in production of high quality aspheric surfaces. So if you have any questions or you're interested in kind of sourcing an aspheric surface, please reach out to us. We would be happy to take a look at your project and see if it's a good fit with our capabilities. So on the agenda for today, we're going to talk about a couple things. First, a brief introduction to what an Asphere is. So, what is an aspheric surface, and potentially why is that useful? Three of the typical manufacturing processes that surround the production of these aspheric surfaces, and then how to test these aspheric surfaces. So the metrology on these surfaces is a little bit more challenging than your typical plano optics or spherical optics. So we want to discuss some solutions that are out there for kind of measuring these. And then finally, as kind of a wrap up, we're going to talk about, once you have a measurement of these surfaces, some of the typical defects that are involved with these typical manufacturing processes. So what is an aspheric surface and why is it useful? So an aspheric surface, in its most simple definition, is a surface which departs its form, or its top surface departs from a spherical form. So you can see this image just right below that definition of, on the right hand side, your typical spherical surface, and then the red is that departure from that spherical surface. So we typically describe these types of surfaces using an aspheric lens equation or just an aspheric equation. There's a couple different variations of these, but the fundamental constants are pretty consistent throughout a lot of those equations. So you have your aspheric coefficients, your conic constant, base radius of curvature, and all that information is required in order to establish a SAG table or a description of that design. So Zygo's MX software, for those of you that are available, that's kind of our software package that's used to run our instrumentation and then analyze data post-acquisition. The types of job files, or the types of aspheric file descriptions that we are able to describe those surfaces with are listed here, just as a reference point so that you can go back and look at those or kind of configure your design so that it can be imported into MX. So why are they useful? What is the benefit of using an Asphere in your system? And really, there's two main drivers, I would say. You'll see in the lower left-hand image, two optical systems, both essentially performing the same resulting imaging performance. One is used simply with spherical surfaces, spherical lens elements, and the bottom image is one that has been leveraging aspheric surfaces in its lens design. And so you can see that there's less optics. It's a 5-optic system versus a 3-optic system, which saves you on your overall size of the package, the weight of the package, and generally the cost of that overall system. So another benefit could be the improved aberration reduction of an aspheric lens, or that an aspheric lens can provide. So spherical aberrations, astigmatism, those are two common aberrations that can plague an optical system. And we see in the kind of on the right-hand side image, a design that was created using spherical lenses and one that is using aspheric design. So that spherical aberration allows you to image a system without that distortion. So you get a crisper overall resulting image. So 3 of the main manufacturing methods that I did want to touch on today, just to give some context as to how these surfaces are produced, are going to be aspheric polishing, diamond turning, and you'll hear it be called injection molding or stamping or just molding. And those can be used with kind of glass and polymer surfaces. But starting with aspheric polishing, this is where you're taking a glass substrate and you're rough cutting. It could be a multitude of materials, but typically it's going to be a glass substrate. You're rough cutting that using a CNC grinder, and then you're going through with a small contact polisher that is typically computer controlled, and you are using an abrasive slurry to polish that surface. So that results in a very high quality surface finish, but it's very time consuming, and it can take a lot of iterations to get the exact form that you're looking for. So there's a lot of metrology that is involved where you're taking it to a polisher, measuring the deformation, taking it back to a polisher, And so very high level of form error can be acquired because of some of the finishing techniques that are involved with polishing. So MRF and IBF allows you to reach, optics that have a surface wavefront spec that are very, very tight and controlled, and also a surface roughness that is fairly smooth. The next one that we want to discuss is diamond turning. So this is kind of similar in that it is a mechanical removal of material from the surface of a substrate. The difference being that it is done through a rotational spindle. So diamond turning instruments tend to leverage an air-bearing spindle that is very tight mechanical specs, so that you have a very high level of precision on where you're placing or where you're rotating this substrate. And then a diamond tipped cutting tool is kind of used to remove material as it translates across the substrate. And you can achieve a very high level of surface finish with this technique, but at a faster rate than your traditional polishing method. So this is very good for kind of higher volume applications. One of the things that may be something to look out for when using diamond turning is if your application is sensitive to mid-spatial frequencies. That's going to be something where you want to know if that's going to be the case and identify if the level of mid-spatials in a diamond turned optic are going to plague your application. So we'll talk a little bit about that a little bit later on when we're talking about some of the manufacturing artifacts or manufacturing defects that can present themselves from some of these methods. And then finally, we have molding. So molding is really good for high volume, where typically you'll see it in something like micro lenses or kind of where there's much higher volume, or there's a higher demand for the number of optics that need to be produced, but maybe not at the extreme levels of quality that, say, a diamond turning or aspheric polishing would require. So the essence of this manufacturing method is that you're taking a semi-liquid / semi-solid material, and you're either stamping that or injecting it into a pressurized die or a mold to take the form of that die or a mold. And then that material, once it is filling up the entirety of that mold, it's either cooled and kind of hardened into place, or it is cured. Some materials can be cured using a UV light to take the same shape as that mold. So again, it's a great application for high volumes, but because of the material properties involved in this method, it can be tricky. You can be prone to kind of wear and tear on the mold plates that need to be reworked with time. There's a fairly large startup cost involved with molding or injection molding technique. And then, yes, thermal cooling, or kind of the properties as you're curing that material can result in some kind of unwanted geometries. So why are Aspheres difficult to measure? Interferometry is a comparative measurement. So you'll see in the kind of top right image, you have a spherical transmission element that is installed into your Zygo interferometer. And this creates a spherical wavefront that you can then catch on a resulting spherical surface. You kind of adjust the position of that optic in free space to where that wavefront matches the prescription of your spherical surface. The same is true for plano. So you're taking a plano wavefront and reflecting that off of a plano part. In the case of Aspheres, because there is that departure from a spherical wavefront, you quickly approach the slope capture limit of the instrument. There's too much departure from that spherical form. You can get away with mild Aspheres occasionally, but typically you're going to be outside of, again, that slope capture limit. And so you need to adjust your wavefront or kind of manipulate the position of that wavefront in a way so that you can measure the entire Asphere. And so again, with our Optical Profiler product line, it may have the slope capture limit, but it's a smaller field of view. So you don't necessarily have the ability to capture the entirety of some larger Aspheres without doing some stitching and some pretty creative stitching methods that we will also talk about a little bit later in the presentation when we discuss our Compass product line. So why do we have to use interferometry? And you might think, you know, I have a stylus or I have something that I can drag across the surface. Well, when you're dealing with a very high level of precision, or maybe some softer materials like polymers that are involved in your molding techniques, dragging a stylus across that surface can actually damage the part, and you don't want to damage your final product. It's not going to you know, go over too well with your customers. So, and we'll look at some of those artifacts of what a stylus can do to, say, a diamond turned optic or a polymer optic a little bit later when we discuss those defects. So Zygo in its profile has 3 aspheric measurement solutions that we offer. And those that we're going to talk about over the next couple slides are going to be our Verifire Asphere Plus, our Zygo Compass, and also computer-generated holograms. And so computer-generated holograms and the Verifire Asphere Plus are going to be talked about at the same time because they are very compatible with each other, along with some of the other large aperture systems that are found in Zygo's Laser Interferometer product line. So starting with the Verifire Asphere Plus, those of you that are familiar with Zygo will recognize this tool. It's a fresh take on our legacy VFA that was a Metro Pro-based instrument, which is our old legacy software package. And so we've really taken a fresh look at updating this platform, bringing it up to Windows 10, putting it on our new MX software, and integrating a lot of the aspheric utilities directly inside of that software package. So it's fax flexible, and the ease of use is really a big focus with this new generation of products. So I have a video a little bit later in the slides that showcase an alignment and a measurement of this Asphere. And I think you'll be pretty impressed with how hands-off the tool really has become from its earlier you know, VFA older brother. And so this instrument also has direct CGH tooling that's integrated into the vertical cavity that you see there in front of you, as well as having the latest and greatest generation of our Verifire interferometer as its you know, acquisition supply that you see mounted there on the top of the instrument. So before we get into kind of how the instrument is measured, it measures an Asphere, we want to talk a little bit about actually setting up an Asphere within MX and kind of the utilities that we've added. You know, I discussed that this has been kind of updated from our legacy Metro Pro software to be brought over to our MX software. And so the screen that you see in front of you here is really one of the largest additions and improvements that make measuring these Aspheres a breeze. And so the tool is based off the principle of design files. So you have your aspheric equation that we discussed about on the first couple of slides, and that's, you know, including your aspheric coefficients, your base radius of curvature, and basically all of the variables that are required in order to properly describe that surface. So that information, once it's known, can be loaded into MX, and it gives you kind of an overall sag table that you're seeing over on the right-hand side of your image, but also a measurability of that aspheric surface. So you'll see along the bottom of this software package, a lot of these green checks with top recommendations. This is essentially giving the user a direct feedback as to what hardware configuration is recommended to have the lowest number of zones and be the easiest way to acquire and fastest way to acquire surface data across your Asphere. And so you can see you have zoom, mainframe, if you need an aperture converter, an adapter, and a transmission sphere. And then you know that if you have a new design, okay, I need a 4-inch 0.75x series transmission sphere, to be installed. And so this is really kind of the preliminary setup for measuring that Asphere to make sure your instrument is in the proper configuration. So once it's installed and kind of you have your Asphere loaded into the instrument itself, and you're ready to measure, we've really simplified kind of the way that the instrument is going about taking those acquisitions. So we'll talk a little bit about the principles of how the measurement works, and then I will, again, I mentioned showcase what a live measurement looks like. But essentially, you're taking a spherical wavefront that is going to be sent out from your transmission sphere. And at different points in Z, you're going to get different annulus zones that are going to be in focus. And so we call these essentially that, annulus zones. So we're adjusting the displacement of your Asphere relative to that transmitted spherical wavefront, and measuring at different locations as we step in Z. And so we also control very precisely the location of the part with 2 displacement measuring interferometers that are able to tell the instrument exactly where in Z that part is being held. And then once all of these different zones, you've taken a phase shift measurement at each one of these zones, collected that annulus data, they're then restitched with that Z information being taken into account. And the result is that you get a full coverage of the surface form of your aspheric surface. And so we're tracking the vertex. I'll give you a video demonstration of exactly what that alignment looks like and kind of the base principles. And so the start of each measurement, you need to set a cat's eye position. So the cat's eye position is essentially where the transmission sphere is coming to a focal point. We want to match that focal point up with the top surface or the vertex surface of the Asphere. And that's, you can either call it a focal point or a cat's eye position. We call it cat's eye. As you see on the screen here, there's an interference pattern that resembles what a cat's eye would look like, or kind of a yin-yang. And so what the instrument's doing here is it's captured that cat's eye position, and then it's moving to some of those auxiliary zones to do a alignment. So you can see that there's a decentration of the fringe pattern as it's walking through this alignment process, and then it's going to take out that error that's in the alignment. And basically what that is the offset of the optical axis to the optical axis of the Asphere from the optical axis of the instrument itself. I apologize, the mechanical axis of the instrument itself. So once it has that alignment done, what we're seeing right now is it's actually stepping through each one of those vertical zones, and it's acquiring an acquisition at each one of those. And once those zones have been acquired, you get a resulting image, you get a measurement repeatability that we're seeing in the top right corner, and then a deviation from your overall form. So we subtract out that 3D prescription to see what the residual is that's left over after your best fit has been removed. So again, in the screen that we're seeing right here, you have your sag, which is the actual surface that was measured. Your top right-hand corner is going to be the deviation from design. And then really a nice feature that we've also added is a rotational variation. So what we do in that is we actually remove the deviation form as we sweep a slice radially and get a mean overall form for the surface. We subtract that so that we can identify if there is any rotational variance in the part itself, so that you can help. Maybe it's a diamond turning optic that you're producing, and this will indicate that you may have something that's happening when the spindle is at a 9 o'clock position or a 2 o'clock position, so that you can identify that and kind of make those adjustments that you need to make in your manufacturing process. Same could be true for, say, an aspheric polisher or even a mold plate. It just allows you to see if there's going to be any variation. So a little bit about kind of how the streamlined process has been improved. It's really a three-step process that we've taken the old VFA platform and pushed the VFA Plus platform to. And that is, again, loading your design file. You need to set your cat's eye position, which we discussed is the kind of focal point of where it's going to hit the apex of that aspheric lens, and then really hit measure. And the measure button is going to walk through and essentially do the alignment. It's going to do the test of each one of those zones, and then it's going to provide that resulting image at the end. Another nice feature that has been added and updated into the software is the ability to track your different zones or where you are at actively in the measurement. So if you have a 60 zone measurement or a 40 zone measurement, you know exactly when that acquisition is going to end and if where it is throughout that process. And that's the image that you're seeing kind of in that lower right-hand corner. So like all of our tools and all of our software packages on any one of the instruments, all of those same surface processing steps or surface processing techniques that are available on, say, our Optical Profiler or some of our other laser interferometers are still made available on the same Asphere Plus platform. So you have your subtraction of calibration files, your auto aperture, your bandpass filters as Zernike fits to the surface, so that you can interface with those third-party softwares or be able to analyze your surface for the content of certain defects or levels of aberrations that you're interested in quantifying. Another nice feature that's specific to the Asphere Plus, the Verifire Asphere Plus, is going to be the ability to image the individual zones independent of each other. So if you want to load zone 4 or 5, or you believe that there may be some data quality issues, you can load that individual zone and get information like the vertex uncertainty or the reliability of that measurement. You can also, identify if there's going to be an excess of, vibration that may have presented itself in the measurement if someone bumped the instrument, or if there's data quality issues with dropouts, so that you can know exactly where it is and if it's a good idea to remeasure at that point. So it just gives you a better, a secondary assurance that the quality of your data is exactly, you're measuring exactly as the result is being pushed out. So I noticed that we have kind of a couple quite a couple questions that have been entered into the GoToWebinar, and I think now is probably a good time to stop for a quick Q&A break. So I'll have Aaron kind of read off some of the questions, select a couple of the questions that are in that chat.
Absolutely. Thanks, Matt. I'll start with a comment that we got. Sounds like we're having, so apologies to everybody listening, a little bit of audio going in and out. So Matt, if you can try to keep proximity to the microphone, might help a little bit. The other thing, first question we got that we'll talk about is actually about the VFA and what kind of the range of part sizes or the maximum part size that you can measure with a VFA Plus.
Yeah, that's a good question. So we have our, as I mentioned earlier, the measurability, the design that you can load that design into MX. So if you have the overall aspheric coefficients that are used to describe that surface, that information can be loaded directly into MX, and it's going to give you an idea of kind of if it is going to be measurable or not. And this is going to be something that varies if it's a convex or a concave asphere, or generally, what kind of surface that you're looking at. And so really we encourage you, if you do have any questions or you want to see if your asphere is measurable, please reach out to us. We're always interested, and we can run that information through our software package or provide you with the ability to do so. But generally, as a rule of thumb, 10 millimeters to about 8 inches. We can extend beyond 8 inches depending on the design, but that's generally where the Verifire Asphere Plus is really meant to kind of support. So again, it depends on your design, I guess, is the short reply to that answer.
Sounds good. And then another question is asked about if we have the ability to measure more complicated surfaces like freeforms?
That's actually a great question. That was one of the topics that I know I had mentioned a little bit earlier, and in fact, I think I will go to the next slide just so that we can start to discuss that. Freeform optics, optics that are maybe more challenging aspheric surfaces, or something that's not rotationally symmetric, you know, some of those things that are a little bit more challenging, you know, such as your freeforms, those can be measured with the use of CGHs. So I had mentioned earlier that our Verifire Asphere Plus has integrated CGH mounting that is added into the platform. And so what this effectively does is it leverages a standard spherical or plano wavefront and then manipulates that wavefront to match the expected design of that aspheric test part. So this is not only compatible with the Verifire Asphere Plus, it's worth noting that this also works in a horizontal configuration with our standard interferometers. So if you have an existing Verifire GPI, something that's set up on a horizontal bench, we encourage you guys to reach out if you're trying to test these more challenging surfaces and you're interested in learning more about these CGHs. So what is a CGH in principle? So a CGH is a computer-generated hologram that is essentially, like I said, used with a transmission flat or a sphere, accepts that transmission flat or sphere, and then deviates the beam path to match exactly to, you know, you hold your part in a specific position in Z space relative to your CGH, and that wavefront will be an identical match to the design that you are you're trying to achieve. And so this allows you to visualize the deviation from a perfect aspheric surface. And again, it's essentially performing a similar task as our standard kind of Verifire Asphere Plus in the ability to, you know, visualize a deviation map and then correct for that in your process, whether that be with, you know, a contact polisher or however the production method that you are using to produce that surface. So it is worth noting that a CGH is not something that can be adapted to, you know, one CGH is really made specifically to be used with a singular aspheric design. So for each one of those, you know, complex surfaces, you are going to need its own CGH to interface with that design. So the next overall solution for measuring aspheric surfaces, and this is really focused on some of the smaller optics that you may work with. So under 10 millimeters, this is going to present itself in things like cell phone lenses or the lenses that you tend to find in automotive cameras, also LiDAR applications. You'll see some of these smaller lenses that present themselves. And so this instrument, because of those smaller lenses, it doesn't necessarily make sense to use a large aperture tool that has lower spatial resolution to capture that surface information. So what we've done is we've taken the optical profiling platform that we have, and we have kind of built a system around some of the problems that surround micro lenses. And so to discuss some of those typical measurements that are really key and important to the metrology surrounding those. With these smaller lenses, positioning is really an important thing. You're talking about loading micro lenses into small housings. It's very important that you get the position of these lenses correct because they tend to be nested either into mechanical datums or other optics that have datums that nest upon each other. And so if these datums have too much tilt or they're not centered properly, it's going to drastically reduce the overall performance of that lens system. And so you really, this is something that makes the Compass product unique in its ability to have datum characterization and really adjust for a lot of the problems that can present themselves in this. In addition to those kind of measurements, you're also getting a full 3D surface map similar to the Verifire Asphere Plus where you can do deviation analysis, but also get, because it's a higher spatial resolution instrument, you're talking about smaller field of views and the ability to resolve things like surface roughness. So you can remove the overall form of that aspheric surface and really get the texture information. And so that, that's also helpful in the performance of that lens. So again, I mentioned that this is leveraging one of our 3D surface profilers, but with a kind of an advanced staging solution, so that you're always keeping the surface of that asphere kind of normal to the optical axis of the instrument. And then you're rotating that part and translating it radially so that you can basically re-stitch the entire surface and remap the entire surface of that component. So the technology is CSI. I know I have it written here. That is coherent scanning interferometry, which is slightly different from our standard large aperture systems. And if you're looking to gain some more information about our optical profiling product line, or just the differences between a Fizeau style interferometer that we provide and a CSI optical profiler, again, please reach out to your local rep or myself, or log that information into the chat, and we'd be happy to point you towards some existing material that we've put out and just kind of go deeper into explanation on that. So finally, this brings us to some of the defects that are going to be surrounding these test methods, or manufacturing methods, pardon. And that is going to be, let's start with the first one, I guess, and first and foremost one, which is going to be the most typical thing that people are looking for. And that's going to be acquiring an overall sag map of what your aspheric surface looks like. So the 3D form of what your actual surface that's been measured. And then using that aspheric equation, you can back that information out. And what we see over on the right-hand side is actually a deviation from that aspheric design. So you can see that there is, we kind of call it some potato chipping or some saddling in the production method. And so that's useful information to kind of target in on what that causation could be, and potentially how to back that information out, or back that polishing or that diamond turning or molding feature out of your final product. So the next thing that I do want to discuss is really going to be contamination or kind of small defect inspection. And so on the image over on the right-hand side, we're seeing two different types of defects. We're seeing a diamond turning mark, which coming back to those earlier slides when I was discussing the manufacturing method of diamond turning, these are kind of the mid-spatial frequencies that you would tend to see on a part that has been diamond turned. So these concentric rings, and that's something that, depending on your application, again, may be something that you have to look out for if it's presenting itself in your product, and adjust your diamond turning instrument so that you're kind of minimizing the effect of this kind of what we call mid-spatial frequency. The other thing is surface contamination. So any manufacturing method is going to use some form of slurry or lubrication, or maybe there's some residual material residue that is left over on your product, or even oils from part handling or cleaning supplies. Those things can all be residual, and that's not something that you want to pass off onto your customer, but it is something that is identifiable, maybe not to the naked eye, but to our instrument once you take an acquisition of that surface. And so, that allows you to control, quality control of what is going to be shipping out of the building, and identifying if it's something that maybe it's just a smudge, or maybe it's an actual defect that has been printed onto your surface. So this is kind of a useful tool for analyzing those things. So now kind of a manufacturing method specific set of defects. So these two images we'll see here, left and right, are going to be both diamond turned products, or diamond turned surfaces. And so we see a couple different artifacts from the left hand image to the right hand image. And starting with the left hand image, you're going to see your typical mid-spatials that we were talking about earlier. These concentric rings can also be seen on the right-hand side. But when you're taking a look at the right-hand side image, you also see kind of a center, almost high spot that transitions into a low spot. And so we call this kind of feature a pip in the diamond turning industry, and that is essentially when the optical axis of the optic hasn't been necessarily perfectly aligned to the spindle or the cutting tool position. And what you end up getting is, either that high kind of a nipple type feature in the center towards your vertex, or a dimple type feature in the center towards your vertex position. And so that can be kind of identified and calculated what that tool offset is, what the kind of misalignment of those two axes are. And then that will help you to adjust and dial in exactly where your tool setup is, so that you're starting or finishing exactly at the center position of your optic. And again, that's a tool offset result that's available inside of MX. We also see in the left-hand image, I know I mentioned it earlier, as to kind of some of the reasons why you would want to measure an Asphere using a non-contact method. So we're seeing some scratches that were actually left over on a high quality diamond turned optic. When you go ahead and kind of trace across that surface using a contact profiler to get the overall sag table from that surface, it's leaving a scratch or a clean line into that material. And again, that could be done with any optical surface that you're going to be dragging a tip across. So really, you spend all this time putting this hard work in to produce an optic, and then you don't want to, cause damage to that surface in your measuring process. That's, you're already giving your customer something that is, less than what you are capable of producing. So next, we wanted to talk a little bit about injection molding specific defects, and you'll see kind of a missing apex. What this can be is, maybe the material properties while the injection molding process was going, maybe there wasn't enough material, or it wasn't heated up to a high enough temperature, or, any of the various number of reasons why a material wouldn't fill out the entirety of a mold. And we're talking about something that, you're really only missing, less than a micron. It's from the form of the surface. You're only missing a couple hundred nanometers of actual material from this surface at the vertex. And that is, can affect the performance of that lens system, but it's not something that you would be able to pick up without the metrology surrounding it. So, in measuring that surface, it's, obviously very clear that you can see there is a missing amount of material from that's reducing the ability to hit that target aspheric design. So again, a couple more molded lens defects that can tend to present themselves. Starting on the left-hand side, figure 1 and 2, we'll see a surface with form removed, so that you're really looking at kind of the structure of that surface. And it's very difficult to actually notice the scratch that we can clearly see in figure 2 in figure 1. It's there and you can see it, but it's hard to put a spec on that data or to basically highlight that information. So one of the tools that's available inside of MX is a slope capture limit. And so you can set your tolerances, and this can be a good indication of when you need to rework your molds, or to identify if there has been some damage that's been suffered and maybe printing into your sample and affecting the performance of that lens. So you can clearly see, as we do a slope filter, this deep scratch that's contained in the die cup is being highlighted by this slope limit that we've set, and really will give an operator, if you're going back and checking that once a month or once a week, or just to ensure quality, it'll highlight that maybe that mold or that die cup needs to be reworked and reprocessed, so that it's not going to be affecting the final results. And then on a similar topic of flow through material, we'll see that in the image on the right-hand side, there was obviously a bubble that had collapsed in on itself, leaving a void in the surface. And so this was a case where a customer is complaining about the performance of his lens, sends some samples in, and we can clearly see what is the causation or the limitation of the performance. You know, you have about I'd say 8 micron or 0.8 micron gap or void in the material, and that's going to affect the wavefront that's passing through that section of the material, so that it's, you know, limiting your imaging performance. So again, that's kind of the bulk of the material, but I did want to stop at one more point in our webinar today, just for another quick Q&A session to answer some of those questions that I've seen kind of coming in throughout the webinar today.
Thanks, Matt. I want to thank everybody attending, because we've actually gotten a ton of questions in the chat. I know we're a little bit over time, so I'm only going to give Matt a couple of quick ones. I've tried to respond to some of them already. If I have not responded to you yet, you will definitely be getting a response from me or somebody else on our team shortly after this webinar. So one that I have for you, Matt, you mentioned that CGHs are designed for a specific reference optic. How about with the VFA? Is there a specific sphere you need to use with each part for the VFA Plus?
Yeah, so both, you know, as we mentioned with CGHs, everything is going to be specific, you know, requiring either a transmission sphere or a transmission flat, but also with the optic itself that you're trying to test. In that measurability tab that we mentioned early in the presentation, that's going to give you exactly what F number, both what diameter and what F number transmission sphere is going to be required in order to measure your aspheric design. And so with, you know, the information like the base radius of curvature and the overall diameter of your part, that's going to be a big driver as to what F number transmission sphere you're going to need to pair up with that surface in order to have the best chance of 100% measurability on that part.
Sounds good. The other thing that I wanted to bring up to you real quick, because I think it's a good group one, is somebody asked about measuring torics. How do you measure a toric?
So torics is actually something that you would think that my response would be that you need to use a CGH to measure a toric. It's one of those complex wavefronts. But there's actually a toric utility that's built directly into the Verifire Asphere Plus. And so with toric surfaces, you actually have two optical axes. You have a cylindrical optical axis and a spherical optical axis. And so we do a very similar vertex tracking method that we do with your traditional Asphere. However, it's a little bit different because of the wavefront that's coming off of those surfaces. But the base principle that you are going to be stepping in Z surrounding both of those optical axes and collecting zone information is still going to be the same. So that is something that is an available package that is embedded directly into MX software and supported by the Verifire Asphere Plus.
Awesome. Thank you. As I mentioned, if I haven't either responded to your question in the chat, Matt hasn't answered it live. We are taking note and saving all these, so if you haven't got an answer yet, I promise you'll get one soon. Thanks, Matt.
Thank you. I hope that the audio issue had corrected itself. And if not, again, I wanted to mention, you know, please reach out. If you have any questions surrounding this that maybe were not addressed, we will again leave our information at the end of this presentation. So I did want to make note that, you know, we understand that the pandemic is still going on and COVID-19 is still affecting a lot of companies' travel restrictions. And so travel to our locations is not always going to be something that is going to be available for everyone that's out there. And so we obviously encourage all of you to try to come in for a live demonstration and to see our products. You know, we love giving live demonstrations and really showing off all of our tools. So please, if that's an availability, we'd love to have you. But obviously, like everyone has, we've all gotten very good at using virtual techniques in order to get around some of the challenges that COVID has presented. So, you know, if you're interested in a virtual tour, or a virtual demonstration, by all means, please, you know, reach out. We can set something up so that, you know, it's 90% as good as you being able come on site and actually, get an insight of our product. I've also left some key links that I think are going to be useful directly in association with today's webinar. So spatial resolution related topics. So I know we discussed some mid-spatials, effectively measuring and quantifying defects on surfaces. So if there was something that I didn't necessarily get to today regarding the defects, please, follow any one of these links. And then also, again, just to highlight our manufacturing capabilities, I've attached a link directly to some of the capabilities that are out of our Richmond facility, where we do a lot of our extreme precision optical manufacturing. So again, if you have a question about an Asphere you're trying to produce or measure, reach out. I'm Matt Battistoni out of the Western Regional Office. Aaron McDonald's information below. If if you're not out west or you're not necessarily looking for a product manager, by all means call our main line and we will direct you to your local account manager or your obviously local personnel that's going to be able to help you best. So I know everyone's busy. I do apologize for going over schedule. I wanted to thank everyone for showing up today. Hopefully we addressed everything that's the questions that you had surrounding Aspheres and Zygo's ability to measure some of those surfaces. So again, thank you everyone.